You are welcome to a summary of the blood vessels. Blood vessels are they are tubular structures that carry blood throughout tissues and organs to designated areas. So blood needs to be transported to specific cells, specific tissues. The blood contains oxygen and other nutrients. So how does the blood get there? The blood gets there via tubes that are called blood vessels. These same blood vessels, they take oxygen, poor blood, and other wastes from tissues and cells, and they return that to the general circulatory systems. So think of blood vessels more like roads. Composition. So anatomically, there are four main structural materials that are combined to make a blood vessels. We'll have the fibers, connective tissues, smooth muscles, and endothelial cells. Now, if you go back to A and P1, the reason why we have smooth muscles here, it is because smooth muscles they are under involuntary control. So smooth muscles they contract involuntarily, and this is essential for the movement of blood. So why is it necessary to have blood vessels? I said a couple of seconds back that blood vessels they are like roads. They can take blood to targeted organs. They ensure that movement of blood is not random. So if you dissect a human being and you go in there, you will not find blood just scattered all over the place. This is more like a brief summary here of the functions of blood. There are about say four of them right here, and that's pretty straightforward. Deliver blood to tissues, and this blood contains oxygen and nutrients, and then they take oxygen poor blood away from tissues and also waste away from tissues or cells. That way these tissues or cells they end up not poisoning themselves. And types of blood vessels, we have arteries. So we have arteries, we have capillaries, and then we have veins. So let's talk about arteries first. Arteries from the outside they look reddish. They have thicker walls and they have a smaller lumen. They transport oxygen-rich blood. They transport oxygen-rich blood. Um, the the blood in the arteries is reddish or pinkish. That's because of the abundance of oxygen that is in the blood. Now, arteries are subdivided into arterioles. Arterioles are small subdivisions of arteries, and we can have different divisions of arterioles. We can have different divisions of arterioles. So, for example, over here, this will be one division right here. This will be an arterial, will be an arterial. But if you come over here, this will be another division. So this might be called more like secondary arterioles, and the other one divides. This will be called something like a tertiary arterioles, etc. So if blood has to be delivered to a specific part of an organ, specific tissues in an organ, a specific spot in an organ, a regular artery will be too big to do that distribution because that specific site is very small. So you need a very small vessel to be able to go to that specific site. That's where arterioles actually come in. And the arterioles also, where we have the exchange of substances. So this is a capillary here. It is in a capillary that we actually have exchange of substances. Half of the capillaries is made up of arterioles, and then the other half is made up of venules. We'll talk about that. So this is a spot where you have the active exchange of substances. So on this side, on the reddish side, you're going to have oxygen and nutrients. and on this side over here, you're going to have carbon dioxide and other waste materials. So capillaries, you normally find capillaries between arteries and veins, between arteries. So this is an artery over here, and this is a vein over here. And you can see that we'll have the capillaries in between here. As we said earlier on, they are points for exchange of materials. They are points for exchange of materials. So this portion will have waste products, carbon dioxide. This portion here is going to have oxygen and nutrients and possibly hormones and maybe white blood cells that are transported throughout the body. Veins. So veins, they look bluish outside. They look bluish. So when we see veins through our skin, they look bluish. They transport oxygen poor blood. Now, the blood inside veins does not look bluish. It is dark red. It is dark red. The reason why it looks bluish when we see veins through our skin is because of refraction of light. It's because of the refraction of light. So that is properly exhibited here. This is blood in veins. Oxygen-rich blood is kind of a bright red because of the amount of oxygen in it. The oxygen in veins is dark red because of the carbon dioxide or less oxygen in it. Now, so if you look at we said earlier on, the veins they look bluish outside. That's due to the refraction of light. That if you look at the anatomy carefully as compared to the arteries, the walls are thin. The walls are relatively thinner, and the lumen is relatively larger. So this is a diagram of the arterial system. The responsibility of this system is to ensure that it takes oxygen, poor blood, and waste materials from all parts of the body above and below the heart, returns that blood to the heart so that the heart can actually pump that oxygen poor blood to the lungs where gaseous exchange takes place. So venules are subdivisions. Venules are subdivisions of the veins. So if waste products, carbon dioxide and other waste products, if they have to be picked up from tissues or from cells that are very small, we cannot have a large vein like this actually penetrating or infiltrating a very small tissue or a very small cell. So it is going to be subdivisions of the veins, which are called venules, that can actually penetrate small tissues, and they can go in there and then pick up the oxygen and other waste and then return it to the venous system, where the blood will be sent back to the heart, and then the heart pumps it to the lungs for gaseous exchange. So far we have said that um, arteries they transport oxygen-rich blood, veins they transport oxygen-poor blood. Now, when we put pulmonary in front of arteries, the arteries they carry out the exact opposite of the functions that they are normally ascribed to. So one more time, arteries they transport oxygen-rich blood, but the pulmonary artery transport oxygen-poor blood. Pulmonary here is referring to the lungs. Pulmonary refers to the lungs. So it is the pulmonary arteries that transport oxygen poor blood from the heart to the lungs for gaseous exchange. And you can see that this the pulmonary arteries they receive their blood when the pulmonary semilunar valves opens, when the pulmonary semilunar valves open, which is associated with the right ventricle. Pulmonary veins. So again, veins, they normally carry oxygen poor blood. They want us to have pulmonary in front of that. Then these veins, they carry oxygen rich blood. They transport oxygen rich blood from the lungs back to the heart, and that's going to be the left atrium, if you're looking at models of this, or diagrams of this, you will see that the pulmonary veins, you'll be able to see that a pulmonary vein is actually going to have thin walls, large lumen, and then the pulmonary artery is going to have thick walls and a relatively smaller lumen or cavity. The pulmonary circuit actually has to do with it's made up of the pulmonary arteries and pulmonary veins. These are vessels that are associated with pulmonary circulation. Pulmonary circulation here means circulation in the lungs, and as we said before, uh, we need where the we need oxygen rich blood from the lungs to be transported back to the heart, and then we need oxygen poor blood, and then we need oxygen poor blood from the heart to be transported to the lungs. So these two transport vessels here, they constitute the pulmonary circuit. Look at anatomy of blood vessels. So a normal vein or a normal artery actually has three wall layers. If you look at their walls, they have three layers, and the layers are called tunicas. The layers are called tunicas. Now, tunica, the first wall, the outer wall of the tunica is called the tunica externa or the adventitia. It is protective, it's used for anchorage, it's made up of collagen and elastic fibers, and it also functions in shock absorption. Of course, it also provides structural support, and it prevents the vessel from expanding more than what it's actually supposed to be. If a vessel expands, which is what we call vasodilation, if it over vasodilate, it may actually affect blood pressure relationships. The tunica media is the middle layer, and most of the time it is the thickest of them all. Is the thickest of them all. This layer is very important. It is capable of vasoconstricting and vasodilating. When a vasoconstrict, it reduces the flow of blood. When it vasodilates, it increases the flow of blood. If you guys go back to when we did hemostasis under blood, you can see the importance of vasoconstriction and vasodilation. So, for example, if you are bleeding somewhere in your body, then you expect the vessel in that part of the body to vasoconstrict. If you are exercising where you need more oxygen to be supplied to your cells, which means more blood supplied to your cells and tissues, you need the vessels in that part of the body to vasodilate. And because the tunica media can increase or decrease the diameter of a blood vessel, so it does have the potential of actually regulating or affecting blood flow and blood pressure. The tunica intima sometimes is also called the tunica interna. This is the layer of the blood vessel that is in direct contact. It is in direct contact with the blood, and it is associated with friction between the blood and the containing vessel. So it ensures that it reduces friction between the blood and the containing vessel, which is the smooth muscle tube. So if we reduce the friction, blood will flow easier. If the friction increases, blood will flow with difficulties. Oftentimes, when blood is flowing with difficulties, then the heart may start pumping harder and faster. And when the heart starts pumping harder and faster, that may bring about high blood pressure. Valves, right? So valves, we only have valves in veins. We do not have valves in arteries. So that's one main anatomical difference between veins and valves. The reason why we need to have we need to have valves in veins is because, before we look at that, uh, what is the main function of a valve? Valves control flow in one direction. Valves control flow in one direction and they prevent backflow. So um, the oxygen poor blood that is returned to the heart, oftentimes it does so against gravity. So while gravity is trying to pull the blood down, but it has to go up to the heart. So if you have valves, when they open, then blood will flow upwards, and then the valves will close. And then when it close, it prevents the blood from actually moving downwards via gravity. And another way that blood actually flows upward in the veins is that blood vessels, they are normally embedded within skeletal muscles. So when the skeletal muscles contract, it squeezes the blood vessel in it, and then when it squeezes it, and then the blood moves upward, and then luckily that the vessels, they have a valve, and then when the skeletal muscle squeezes, when it contracts and it squeezes its smooth muscles, which is the blood vessel, the valves will open, blood will move upwards, and then when the skeletal muscle that surrounds the blood vessel, when it relaxes, then the valve is actually going to close, preventing the blood from moving backwards. So this was another good example here of a diagram of how valves actually function. All right, we are still continuing our journey of the anatomy of the of blood vessels. We have the lumen. So when we go past the walls or the tunica externa, tunica media, and the tunica interna, and then we'll go to the lumen. Lumen, that is where blood is actually stored, and it also provide a pathway for blood to actually flow. This is a good table here that summarizes, kind of say, veins, vessels, arteries. Over here, it gives us the future, then here it is for the veins, and here it's for the arteries. I think it is self-explanatory. These are just some diagrams that these are just some diagrams that we have here. They they show us differences between arteries and veins. You can see here smaller lumen, larger lumen, thicker walls, thinner walls, valve, no valve. Now, more diagrams here. More diagrams again. Here you can see thick walls, small lumen, large lumen, relatively thinner wall. The great vessels. We saw the great vessels when we actually looked at the heart, and the reason why they're called great vessels, there are a couple of reasons why they're called great vessels. You can go back and check your lecture on the heart. But they are the largest vessels in the body. They are directly connected to the heart. They are actually either taking blood away from the heart, or they are the ones that are directly depositing blood into the heart. Now, there are three main groups of Great vessels, again, this is a revision here. We'll have the aorta and the subdivisions of the aorta. They are the ascending aorta, aortic arch, descending aorta. And then we'll have the venae cavae, superior and inferior. Then we'll have the pulmonaries. We'll have the pulmonaries. So we'll have the pulmonary arteries and the pulmonary veins. So for example, we know that the aorta is the source of oxygen-rich blood to all parts of the body. The source of oxygen-rich blood to all parts of the body. So when oxygen-rich blood is pumped out of the left ventricles, it enters the aorta, and then some of it is will be channeled via the aortic arches to the neck, the head, the brain, and then the descending aorta distributes blood to all the rest of that part of the body that are below the heart. So we've talked about this already. So this is the arch right here. So if you see this carefully, the ascending aorta is the heart pumps the blood directly into the ascending aorta, and then from the ascending aorta it moves on to the arch, and then from the arch some of it actually goes to the superior portions of the body, and the rest of it continues down the descending aorta to the lower parts of the body. Right, this is just reiterating what you just said. The superior vena cava, it drains blood, it drains oxygen poor blood, anything above the heart and then back to the heart. And of course, it drains that via the blood that it contains from the superior portion of the body will be drained into the right atrium. If you know the inferior vena cava, on the other hand, it drains all parts of the body below the heart, the lower limbs, the abdominal region. It drains them of oxygen-rich, oxygen-poor blood, and then it sends that blood back to the heart, specifically to the right atrium, where it will pump down to the right ventricle and then to be pumped to the lungs for gaseous exchange. We already talked about the pulmonary arteries. They carry oxygen for blood to the lungs from the right ventricle. Pulmonary veins, they carry oxygen rich blood from the lungs back to the heart via the left atrium. Now, this is more like some good reading for yourself. We need you to know some of the main vessels of the lower limbs, because arteries and veins, for the most part, they are parallel to each other. They transport blood in opposite directions. So sometimes, for the most part, if you know the name of the arteries, you end up knowing the name of the vein. So if you take, for example, here, the you see the common iliac artery. You have the external and you have the internal. You can see that here, and then we have the common iliac vein side by side. You have the external and you have the internal. All right, the thorax as well. The thorax and the upper limbs. I need you to be able to actually know this. I want to test you to see whether you know the main transport vessels, the larger transport vessels in the major parts of the bodies. Now, besides the major parts of the body, I also need you to know the major arteries and veins that are associated with blood flow in some of the larger organs of the body. So, for example, in the kidney here, it's going to be the renal artery and the renal vein. Renal artery and renal. And then you have the liver. Then you have let's look at the heart artery. So we have the the blood that is pumped out of the heart, the oxygen-rich blood that is pumped out of the heart, is normally it is not used by the heart. So before, as the blood is being pumped out of the heart, this is the ascending aorta right here. The coronary arteries, they tap some of that blood back into the heart. So the blood that the heart itself uses, it comes from the coronary arteries. You can see the left and the right over there, and they are tapped from the base of the aorta. Um, the same kind of goes for the heart veins as well. These are the coronary veins. They are responsible for picking up oxygen poor blood in the heart itself, and they return that oxygen poor blood to the vena cava that will now deposit that blood or transport that blood to the right atrium, and then it will pump down to the right ventricle where it will be pumped out into the lungs. Brain vessels, again, I just want you to know some of the main arteries of the brain, main arteries of the brain, and then the main veins of the brain as well. The same with the lungs. We talked about the pulmonaries already, so I think that one is fairly familiar. The small intestine. So you have to be in a position where if you are giving examples, will you know that these are major arteries of the small intestine. These are major veins of the small intestine or the large intestine, as the case may be, pancreas, as the case may be. Um, Pulmonary circulation. We've kind of touched about this. Every time you see pulmonary, it has to do with the lungs, So, um, oxygen poor blood is transported from the RV to the lungs for oxygenation, or more correctly for gaseous exchange. And then oxygen poor blood from the vena cava will enter the right atrium, right? Enter the so the superior vena cava and the inferior vena cava, they carry oxygen poor blood. They'll deposit their blood in the RA, and then the blood in the RA will be pumped down to the RV through the tricuspid valve. And then blood will be transported from the RV to the lungs through the PSLV, pulmonary semi-lunar valve. And then when it goes to the lungs, then there will be exchange. The carbon dioxide will be exchanged for oxygen. Then the blood becomes oxygen-rich blood. Now it takes us to the systemic circulation. Now this oxygen-rich blood that actually has nutrients also will be pumped back into the heart through the left atrium, and then from the left atrium it will be pumped down to the left ventricle, and then from the left ventricle it will be pumped into the aorta, and then from the aorta the blood is actually going to be transported throughout the body. Right, we just talked about that. Um, Again, coronary circulation, we've touched on this. Essentially, the reason why you see that we have coronary circulation, these are the vessels that are dedicated to distributing blood or circulating blood within the heart itself. The heart has the responsibility of circulating blood to all parts of the body, but that blood is not benefiting the heart. So the heart must have its own circulatory system that supplies blood to it. That's what is called the coronary circulation. So every time you hear coronary, we are talking about the heart. There are two main vessels. We'll have the coronary arteries right here, and we'll have the coronary vein right here. So the coronary arteries, they circulate oxygen-rich blood, while the coronary veins, or sometimes they are called cardiac veins, they scoop up oxygen-poor blood and they return that to the venous circulation. Um, Coronary bypass surgery. Now, sometimes one of the smaller arterial vessels right here, or it's one of the small coronary vessels like here in the heart, they may be blocked. And if they are blocked, the portion below the blockage will not be able to receive oxygen rich blood and the other necessary nutrients. Now, if that is not, if that blockage is not able to be dislodged, then what they'll do a coronary bypass surgery. They'll take tubes that are very similar to actual blood vessels, and blood will be tapped from any part from the aorta. Blood will be tapped from the aorta, for the most part around the ascending region of the aorta and the arch. Blood will be tapped from there and then connected back to the heart. But it is going to be from artery to artery, artery to artery. So if we have just this is a single one, so we have just one tapping back to the heart. If we have two, then that will be called double bypass. If we have three, that will be called triple bypass. Now, the reason why this is important is because if cells are deprived of oxygen-rich blood for a prolonged period of time, then those cells will start dying. And when they start dying, that's what is called a heart attack or myocardial infarction. These are just some good diagrams for blood circulation. Um, anastomosis. Anastomosis is when an area may be blocked and blood is actually not flowing to that area, so the blood vessels may be blocked and blood is not flowing around that area. Then some alternative route may be found through which you can bypass the blockage. You can actually bypass the blockage so that the areas after the blockage can continue to actually have blood supply as needed. Good diagrams here for you. Um, so blood pressure is a measure of resistance to blood flow. Blood pressure is a measure of resistance to blood flow. It's measured in millimeters mercury. These are the three sources of resistance to blood flow. If the blood is thick, if the blood is thicker than normal, it will resist normal flow. If the blood vessel is longer, is longer than normal, then there's going to be more resistance. In other words, the persons who are very, very tall, there's more resistance to blood flow in their bodies. And then also, the smaller the diameter, the more resistance to blood flow. One way that you can take care of the smaller diameter aspect of it is if you exercise regularly, your blood vessels are going to be more or less permanently dilated. When they are dilated, it means that the blood vessel diameter has actually been increased, and therefore you can this may not actually be much of a problem as compared to people who do not exercise. Right. This is just more examples here to explain blood pressure and diameter of vessel. So this is our normal blood pressure here. So we have 120 millimeters mercury. Systolic pressure, heart contracts, and when the heart contracts, the SLV valves they open. The normal pressure for young healthy people, um, so the normal pressure for young healthy people is going to be uh, when the heart contracts is going to be 120 millimeters mercury. Now, the diastolic pressure is 80 millimeters mercury. That is when the heart relaxes, and in that case, the SLV valve they close. So one more time, when we measure normal blood pressure actually has two figures. The upper figure or the upper value is the systolic pressure when the heart contracts. The lower value is the diastolic pressure when the heart relaxes. So when the heart is relaxing, the SLV valves they close. When the heart is contracting, the SLV valves they open. This makes sense that they open because when the heart is contracting, it is pumping blood out of the heart. So these valves need to be open so that the blood can actually be sent out via the aorta. All right. Again, we've talked about this. We can measure blood pressure. It could be we can use electronic method, or we could use the or could use the non electronic methods in measuring that. All right. So these are just some more diagrams here. They give examples of hypertension, high blood pressure, what the um now we have this where you have hypotension. So these are some signs here for hypotension, signs and symptoms. The body vital organs do not get enough energy. So circulatory shock, we talk of circulatory shock, it is when the body's vital organs are not able, if blood is not flowing normally in your body, you can go into circulatory shock. Remember we have said for females the normal volume of blood is between 4 to 5 liters. For men, it is for males is between 5 to 6 liters. Now, at any point in time, if we do not have enough blood circulating in the body, then that can actually lead to circulatory shock. So we have different scenarios that can actually happen with that. You could check details in the PowerPoint. These are some of the signs of circulatory shock right here: cold, sweaty skin, rapid breathing, blue skin tone, weak or rapid pulse, etc. All right, the pulse pressure. Pulse pressure. So how do we measure pulse pressure? These are pulse pressure. These are some of the vital signs that actually use in the medical field. So we measure the pulse pressure as systolic pressure minus the diastolic pressure. So the difference between those two, um, if it is greater than 40 millimeters mercury, then that will be considered to be unhealthy. So remember, the systolic pressure is 120, the diastolic pressure is 80. So if you do that, you actually get 40. So if you actually get anything out of the range of 40 below or above, then there will seem to be a medical problem. All right. So again, here you can see that if the PP is 60 meters mercury, then it means that you have a medical problem in the making. There's some good diagrams here. The mean arterial pressure. The mean arterial pressure. This is the way it is calculated. It is the average pressure that ensures that blood pumped from the heart continues to circulate throughout the body. Of course, it decreases as it moves from the aorta down to the tips of your limbs. It decreases. So the mean here again is just taking what is the average throughout the body. What is the average throughout the body? Right. Um, for somebody to be considered to be healthy, then your best map range should be anywhere between 70 and 110. If it goes out of that range, then it will be considered that you're not very healthy. Tissue perfusion. Tissue perfusion. Passage of fluid through the circulatory system or lymphatic system to an organ or a tissue. Usually referring to delivery of blood to the capillary sinuses. So you can see this is a very good diagram here that actually illustrates tissue perfusion. So this is uh, this is the interstitial fluid. that's interstitial fluid over there, and then you can see that this is the vessel right here. You can see what moves in, what moves out of the vessels to the tissues, and then what moves from the tissues into the vessels. So know that what is required by the cells or the tissues will leave the blood to the tissues, oxygen and nutrients. And what is waste that is generated by the tissues, water, waste, carbon dioxide, it will leave the tissues back to the blood. All right, again, this is just some more diagrams for self-explanatory. So tissue perfusion delivers oxygen, removes carbon dioxide, etc., etc. Um, so the appropriate TP is essential for the metabolic processes in our body. It's essential for the metabolic processes for our bodies. And so, for example, it is important to resistance to infections. It influences tissue repairs, etc. Again, we talked about this before. A circulatory shock is any condition in which blood volume is inadequate and cannot normally result in blood flow. So if you don't have enough blood in your system, then it means that blood is not reaching all tissues or all organs adequately, or the appropriate amount is not reaching the per unit time, and that could lead to some very serious uh, problems somewhere down the line. And hypovolemic shock, large scale blood loss, elevated heart rate, vasoconstriction. So what the heart will normally do is, if you do not have enough blood circulating in your system, then your heart will can sense that, then you have to start pumping harder and faster, harder and faster, harder and faster. And because you do not have enough blood circulating, where your heart starts pumping harder and faster, it increases the blood pressure. And then because also you do not have enough blood flowing, then your vessels are going to undergo vasoconstriction. So they become smaller than normal. Okay, now extreme vasodilation too can lead to poor circulation. If your vessel become too dilated, then the heart also thinks that enough blood is not being pumped into your body, and that can also lead to a problem as well. So the diameter of your blood vessels, they have to be maintained at a certain level. If they go smaller or they go larger, it causes some problems with circulation. So this is a case of over vasodilation here. You can see this dude here. You can see that he has vessels that they look like pipes as opposed to uh, normal, normal blood vessels. All right. These are some cases of homeostatic imbalances. I think they are pretty straightforward. You can go ahead and actually read that. Um, Cardiogenic shock, heart inefficiency, myocardial damage, myocardial infarct, heart attack, etc. So you can see here that the cells here are actually dying. Whether this is bluish or green, the cells are dying. They are not getting enough oxygen, and once the cells actually start dying, that leads to damage of the brain. All right. Again, we've essentially talked about vascular shocks. It results when BP becomes extremely low. Okay, your blood pressure becomes extremely low again because you do not have enough. You probably do not have enough blood circulating in the body. So the way we've looked at blood pressure so far, it looks as if blood pressure is always bad, but blood pressure is not always bad. These are some main functions here of blood pressure. So the reason why blood is able to actually circulate in our body is because of the normal blood pressure that it takes. All right. Here are some problems that may be associated with blood vessels. We have congenital vascular problems. They normally just manifest in older age. So these are problems that you are born with these problems, but they, for the most part, they do not manifest until when you get older. Atherosclerosis, it's when plaque materials that are deposited around the vessel wall, so it actually ends up making the the diameter of the vessel smaller, and if it becomes smaller, you can actually have white blood cells can become so packed around that area that it actually impedes the flow of blood. So these are what I consider to be the subnormal range of blood pressure. So you see, it actually depends on how old you are. This is considered to be ideal, but that is in the case of youths.